So it's a great pleasure for me to be here today in Russia. I would like to start my talk by thanking the organizing committee and Victor for the nice invitation. And today I am going to tell you a very short and very small story. Just something that was very interesting for me in the past year, and which is about photo-inducing single molecule magnet in spin crossover compound. So I don't know if you... So the first compound that we have been looking at is an old friend for many of you. It's an iron 2 compound that displays spin crossover property. So it's the iron PTZ compound with the PF4 sound. So this is a simple mononuclear complex, so very simple things. So you know, most of you know what is a spin crossover. I will just recall for iron 2 here very shortly. So in iron 2, in the octahedral field, you have two different states accessible. The paramagnetic state, which is S equal 2, and the diamagnetic state, here, iron 2 low spin, that is diamagnetic. And you can switch from one to the other, playing on the experiment, playing on the temperature, playing on the light, on the magnetic field, on the pressure. I think Cameron Kepler have shown also with solvent, and I'm sure there is many other ways to switch. So here this compound is really something that even me can cook, because you can just take iron BF4 salt and in ethanol, which is a solvent I know very well, and you just add some PTZ ligand, also in ethanol, and you just stir them an hour on the nitrogen, and you get a decent yield, about 70%. Maybe just a second, because I'm going to change just the resolution, because it's half of my slide is gone, and I have things at the bottom, so just, I don't know why it's like that. Use this one. Sorry about that. I mean, I should have checked my computer before. Yeah, it's looking better now. Sorry for that. So you have the reference. So this compound has been first made by Asnod, and so it's not a new compound, but you will see why it was interesting for us. So this is all data. It's not mine. This is a beautiful work made by this talented scientist, Silvio de Curtin, Peter Gottlieb, Aspar, Hauser, and Spiron. And what they have shown is this compound has a first order phase transition around 130K between the high spin state of the iron 2 and the low spin state, the diamagnetic. And you can photo excite the low spin state in high spin state. And you can use different light, and you can actually do that below 50K. What they have shown is this compound is actually very photosensitive, so you don't need much light to irradiate this compound. It's very easy to do that. And moreover, what they have shown, this effect is completely reversible, because you can pass from the diamagnetic state, and you can photo-excite with green light, you can get the paramagnetic state, and you can do the reverse thing by using red light. So it's really a very nice compound. The things that attract our attention, and I say our because this is also coming from the discussion with Jeff Long, and he mentioned that the high spin state in this system has a trigonal symmetry. And this trigonal symmetry means that we have a complex that is sitting in an isometry space group. So when you work with single molecule magnet, you know that isometry systems I like them because you can actually reduce the symmetry of your Hamiltonian and then remove this term that is at the origin of the quantum tunneling and the mixing of the ground state. So you can reduce the probability of tunneling by simply having an isometry space. So this is why, at the first, we look back at this compound, because it was crystallizing in the high symmetry space. So if you look at the magnetic properties of this compound that we have remade, they are completely exactly the same as the one published. You have this first surface transition I've shown you in the previous slide. But if we put on this data the crystallographic information, you realize that there are tons of things that has been done, and also the paramagnetic phase is well in this high symmetry space group, but as soon as you go in the diamagnetic state, you come back to a triclinic space group and you reduce the symmetry. So that's nice, but what happened when you shine light in this compound? Actually, as I said, you create the paramagnetic state, and this paramagnetic state relaxes about 50K as published. There's no problem about that. Then people have shown that this photo-induced phase is also triclinic. So it's our idea from the beginning was, because we are not in the field of spin crossover and we didn't know well the literature, obviously. This photo-induced state is actually a symmetry that is lower than what we think. Anyway, we look at the slow relaxation of the magnetization in this photo-induced phase by simply doing AC susceptibility measurements, and you have here the in phase and the out of phase AC susceptibility versus the frequency in these frequency windows. And you see basically nothing. You see just a small increase that is completely independent of the field that you observe. So at the first look, you don't observe any slow relaxation with the windows, with the experimental windows that you have. So that was disappointing. But if you look at the literature a little more, you realize that this compound is absolutely gorgeous, because you can actually create different phases depending on how is the thermal history of this compound. So if you take the compound in the R3 space group at high temperature, and if you simply freeze it as fast as possible to low temperature, then you get a diamagnetic phase. So you have a spin crossover from paramagnetic to diamagnetic state, but the symmetry of the structure is still in the high symmetry space group. Then the question is, what happened when you photoexcite? Of course, you create the paramagnetic state, like that. It's easy on the screen, a little less in the lab. And this photo-induced state relaxes around like 60K. And this photo-induced state was also studied by crystallography. And they found that this phase group is also high symmetry space group, R-3. So we studied the slow relaxation of the magnetization in this state. And basically, if you do this, you don't see anything in zero field. And you can expect that in these S=2 mononuclear complexes. And so, but what happened with field? So, just to, maybe this is very easy for most of you, but I mean, if you apply field, you leave the degeneracy between the states. And you can do that with a controlled manner with a magnetic field. So as I said, you reduce the probability of quantum tunneling in your system. So this is what we have done, and this is the AC out of phase AC susceptibility versus the frequency. At low applied DC field, below 2000 and above 2000 Roche-Tech. So at zero you observe almost nothing, and then you increase the field, and you see the intensity of the relaxation mode increasing, and also going down in frequency. Then if you increase too much, of course, you speed up again the relaxation of your system. And so you have an optimum field that is about 2000 Roche-Tech in this case. So now we have this mode. Let's study its temperature dependence at this particular field that is the optimum to study it in our case. So you have this kind of curve. Remember, this is in the photo-induced state. So you have very little of compound, let's say like 3 milligrams, to make sure you photoexcite the whole thing. And you have here the in phase in the top and out of phase susceptibility versus temperature on the left and frequency dependence on the right. And So you see well the mode here, but you don't have always a maximum of this mode. And this is not so convenient to extract the relaxation time of your system. So there is different ways, we are using different ways. I decided to show you one that is very convenient today. What we did is, what Wolfgang Wensdorfer is doing with the M versus T curve he had for single molecule magnet. We apply a scaling method able to normalize all the curve on the single master curve. So with this method, that is also an approximation, you can extract the relaxation time of your system even if you don't have the maximum. And this is independent of any model in this case. So you get this temperature dependence of the relaxation time. Of course, this is not too linear, obviously, it looks like more a curve. So if you want to take the few less point at the higher temperature, you get an energy gap that is certainly way too small in comparison to the reality, but let's give you an idea of what is the energy gap in this kind of system. And then at low temperature, you cross over to a region that is dominated by quantum effects. So this is actually the first evidence of single molecule magnet propriety in a photo-induced state of a spin crossover system. So now you can play around, you can have fun in the lab in your squid. You can simply take the compound that is in diamagnetic state, so obviously it's not completely diamagnetic because there is a residual paramagnetism of the spin crossover system, but anyway, and you can apply green light, photo-induce your nice slow relaxation, and you can go back almost quantitatively when you have done that once with a red light. And you can do that, you can do that as much as you want. So you see the first excitation works, but after you have some residual that is created, but you keep always the same residual when you have done once. So you can cycle between a single molecule magnet that you can observe in your frequency windows and a compound that is mainly diamagnetic after radiation, for example, in the ray. So this is reversible. It's not surprising because this reversibility has been studied way ago. So you have a mononuclear iron 2 system that is diamagnetic at low temperature. You can actually make it magnetic by applying a green light. Applying a positive magnetic field, you can trap it in one of the two states of your single molecule magnet, S=2. You can reverse the field, so you can inverse the potential in which you are, and you can come back on this state at 850 nanometer. And you can do that completely reversibly, coming this state to here, choosing the right field, changing the field, and changing the light. So you have really three states. You can play around. You can play around using different lights and different magnetic field. So now the question arises, and I'm sure you would like to have an answer. I don't have it actually. Is it quite general? So the first compound we tried works. We were lucky enough to have the second compound we tried that works too. And this compound is completely different from the first one I have shown you. This is a work that David Harris and Jeremy Smith have published like 3 years ago. So it's a compound that is also an iron 2 compound, but this time, due to the ligand around, is in the tetrahedral conformation. This compound is ultra air sensitive. It's very difficult to work with. So it was another challenge because the previous work was quite easy to work with. So this compound has a spin crossover here around 80K. It's reversible. They have studied the crystal structure above and below this spin crossover. They have observed a serious reduction of the bond distances around the iron that are compatible with the energy diagram that they have proposed in their paper. So you have a distorted tetrahedral ligand field, and you have the two states, S=2, S=0, and S=2, and you have a spin crossover in between the two. So very nice compound, a nightmare to work with, but we tried to do exactly the same thing, to see if we could observe this kind of behavior in another spin crossover system. First of all, it was not known if this this compound was photomagnetic or not. So we look at if it was photomagnetic. And this one is nicely photomagnetic. You need more than 10 hours of irradiation on about 3 milligrams. And you have a photomagnetic phase that relaxes at this sweeping rate around 30K. The thing is, when you see this curve, you get scared. Because if you have a compound that relaxes at low temperature like that with this sweeping rate, it means that if you stay here at low temperature, around 10K, which is usually the temperature at which you do the photoexcitation, your compound is relaxing quite fast. So you don't have time to do some kind of fancy AC measurement during days. Okay? So that was the first problem we met. And this is actually why here you have 2.3K and not 1.8 or 1.9K. So if you do this kind of experiments in zero field, you don't see anything. And then you apply a field, you see the mode rising, as in the previous case. And if you go at higher field, it's going up in frequency. But here, the problem, if you do these experiments, you need a few days, maybe a day and a half to 2 days. And your sample is not enough trapped in the high-speed state to be able to do that. So you have to irradiate your compound during the measurements. But you cannot irradiate the compound with the same power that you use during the first irradiation. So basically, you put the maximum you have, you irradiate it 10 hours, and then after, in order to keep it in this state, you put the minimum light you need to keep it as much as possible in this state without eating too much your compound. Because if you are using the same power, you are actually going to eat your compound by 5K, for example. In our case, we were lucky enough that at 1.8K, you can do like 4 or 5 of this curve. So you are able to calibrate the temperature. You use some light, you tune the power, you find out how much heating, how much under temperature it is. You can calibrate the temperature. So we were able to do this measurement under light irradiation, which is usually not what we are doing. We usually irradiate the compound and measure the compound after. So it's a very important detail, and this is technically quite difficult on this air-sensitive compound. So here the optimum field is 1000 Hochstedt. You can do the temperature dependence. So this curve below 2.3K I done after irradiation, and the other are done with a small irradiation to maintain the compound. So from this data, you can actually plot the temperature dependent of the relaxation time, and you have something that is more linear than the previous one at higher temperature, and you get about the same energy gap. This is maybe a luck, but this is like that. And you get the curvature that you can expect with quantum effects taking over. So, this is quite general, probably, and I should say that I don't know, because this is the two first compound that we tried, and since we didn't find any others. So we didn't look too hard, to be honest, but the two others, I think, or three others that we tried didn't work. Okay, so I think I was very fast, so there will be plenty of time for question. So just thanking my group, and I think you probably enjoy the poster of my students that are present in the audience and were present at this conference. I would like to thank a lot to people working on this project with me, Corinne Matonia, for a very important contribution in the photomagnetic measurements, especially for this air-sensitive and not very photo-stable compound. Jeff Long, who is probably the father of the idea to look at the photo-induced state and the slow relaxation in these photo-induced states, and the fantastic PhD student working with him, Xiaowen Fan. Also thanks to Jeremy Smith to have provided us a second compound that was very fun to work with. I would like also to thank my university, the CNRS, my region, national agency, and again the organizing committee for the invitation. I would just like to take 1 or 2 minutes more to talk about the problem that we are mainly all facing, which is helium problem. I think in the US it was probably worse than in other places. Steve, I think you had some kind of problem last year. So, but I don't know, it would be not very useful for you. But for the people who are using a magnetometer, like squid magnetometer or PPMS, I mean, the helium is a very big problem, not only for getting the helium, but also for the price that is rising quite a lot. So we have developed with this French company a system that is actually was implemented on the squid magnetometer that is directly plugged on the DWAR, and that is able to reliquify the helium in life. So you don't basically use helium anymore, and we have, after a certain period of testing, we are now able to use this equipment without any cost of helium. And we, from the expectation that we have, based on the little consumption that we have from the pump, we expect to stay like that during 2 years, and after 2 years to add about 10 liters. So if you're interested by this kind of system, I can give you all the information. Okay, so thank you for your attention, and I'm happy to reply to any question. Thank you.
So Rodolphe, in the iron phosphate